Alright, now we're going to look at one of the biggest applications that we're going to be doing with derivatives, and that is understanding average and instantaneous rate of change. So this is exactly what we've been doing, but now we're putting context to what we're doing. So we want to understand the difference between average and instantaneous rate of change, and understand the relationship between position, velocity, and acceleration, and how they relate to the derivative of a function. So if we have a free-falling object, this is our generic free-falling object equation. So a couple things let's point out. What do some of these things represent? So we have seen this equation before. We used this first semester. S sub 0 is the initial height, or we can think of that as position. V sub 0 is the initial velocity. G is gravity, or more specifically acceleration due to gravity. And this is negative 9.8 meters per second squared, or negative 32.2 feet per second squared. Some of you who may be in physics have seen this before, I'm sure. T is time, and then S of t is then the height or position at some time. A couple things I want to talk about real quick. Velocity. So velocity can be positive, negative, or zero. And the reason why velocity can be positive or negative, because that's the confusing part, is how can you have a negative velocity? Is because velocity has to do with direction. So if something is going down versus up, velocity would be negative versus positive. If something is moving forwards versus backwards, forwards would be positive velocity, backwards would be negative velocity. Whereas when we use the word speed, speed must be positive. So another way to think about that is speed is the absolute value of velocity. Make sense? All right. Okay, now back up to this equation, though. Let's talk about, well, derivatives, right? That's what we're doing. So what is the derivative of S of t? It would be S prime of t, which would be g times t plus v sub 0. Because I'm using my power rule, bring on the 2, and I'm left with gt plus, and this is a constant, that's the variable, so it would be v sub 0. That's going to be useful for our first example. Okay, first example. So a ball is thrown straight down from the top of a 220-foot building with an initial velocity of 22 feet per second. What is the average velocity from time 2.5 to time 3? What is the instantaneous velocity at time 3? What is the acceleration at time 3? What is the velocity after falling 108 feet? Okay, so we need to do a little bit of work here. First thing we're going to do is we're going to write our falling object equation for this problem. So I know in this case S of t, since I see units are in feet, I'm going to use the gravity in terms of feet, is 1/2 times negative 32.2 t squared minus my initial velocity was 22, and it was going down because it was thrown down, so 22t, and then plus 220. I can simplify slightly, so S of t equals Okay, so that's my position equation. Alright, first thing we want to do though is we want to actually find average velocity. So average velocity is something we have found before. Average velocity is going to be slope between 2 points. That should make sense, because when we're talking about velocity, that's how quickly you are changing your position, and this is a position function. So if I find the slope between 2 points, that's my rate of change from the one point to the other, which would then be my velocity. This is why it's important to understand that slope and rate of change are somewhat interchangeable as far as what they represent. Instantaneous velocity, that's going to be my derivative. At a point. So the instantaneous velocity at 3 is going to be the derivative when I plug in 3. Acceleration, that I should be able to understand because it's kind of given to me in the problem. Remember we talked about that. And then the velocity after falling 108 feet. So what are we going to have to do to find that? Well, we're going to have to do a little bit of work, and we're going to have to find how long did it take us to fall 108 feet. And then from there, then we can find the instantaneous velocity at 108 feet. So I want you to pause the video and try to find these pieces of information. Just for organization's sake, I'm going to call this A, call this B, call this C, and call this D. Okay? So pause the video, go ahead and do that. Unpause when you're ready to check. Okay, so part D, the ball is falling at 86.251 feet per second after 108 feet. Part C, ball is accelerating down at 32.2 feet per second squared. Part B, the ball is falling at 118.6 feet per second after 3 seconds. And part A, the average velocity was negative 110.55 feet per second between 2.5 seconds and 3 seconds. How do we come up with that? Good question. So, average velocity was the slope between 2 points. So first I find what is the y value at 2.5 seconds. That is 64.375 feet. What is the y value at 3 seconds? That's 9.1 feet. And remember, this is distance from the ground, so the ball's almost hit the ground at this point. Okay, so then to find the average velocity, we find the slope. So 9.1 minus 64.375 over 3 minus 2.5, and we get negative 110.55 feet per second. So this is where, remember how I keep beating to death this is kind of gruesome, I guess, but the idea of context and how important that is when you're answering a question that has context to it. So we can have a negative velocity, or we could say that it's falling at 110.55 feet per second down. Either one is fine. So in this case, I just said that the average velocity was negative 110.55 feet per second between 2.5 seconds and 3 seconds. So I didn't put in the down because I kept it as negative, but I could have written this as positive and then said that it was falling down. Alright, so the next thing we wanted the instantaneous velocity when t is 3. So in this case, we take the derivative, so v of t, which is the velocity function, equals s prime of t, right? That's the relationship. What is the rate of change of position? It's velocity. Alright, so I found the derivative, negative 32.2 t minus 22, and then I plug in 3. And I get negative 118.6 feet per second. That's my instantaneous velocity, or I can say 118.6 feet per second down. Or in this case, I said the ball is falling, and because I'm using the word falling, that's implying down, because we assume things fall down, at 118.6 feet per second after 3 seconds. So as long as I have that context in here to give me direction, I can write it as a positive number. But it's important that I have that in there. So then the next thing we wanted to do, acceleration. Well, if velocity is the derivative of position, then acceleration is the derivative of velocity. And again, think about what these mean. Derivative is a rate of change. How does your velocity change? Well, if your velocity is constant, You know, like picture yourself driving at 55 miles an hour on the highway because nobody speeds, so you have your cruise control set at 55 miles an hour. You are moving at a constant velocity, so you are not accelerating or decelerating. But as soon as you push on the gas or push on the brake, then you're going to have some sort of acceleration, which is changing your rate of velocity. So it's the rate of change of velocity. So acceleration is the rate of change of velocity. So if I do the derivative of the velocity equation, notice that we just get negative 32.2. So that's a constant. And that also should make sense, again, if we have taken physics. The acceleration due to gravity is a constant. So acceleration is not a constant if you have some sort of thrust behind it, like a rocket or something like that. That's going to not have a constant acceleration. But if it's just a falling object, even though it was thrown down with an initial velocity, the acceleration is still only due to gravity. So that's a constant. So at 3 seconds, that's still negative 32.2 feet per second squared. So the ball is accelerating down at 32.2 feet per second squared. Again, I put in the down part so that I didn't put in the negative part. But I could have just said the ball is accelerating at negative 32.2 feet per second squared as well. You choose, but it needs to be correct. Okay, last one. This one's a little more difficult. We wanted to figure out what is the velocity after falling 108 feet. So first, I need to figure out, well, how high is the object then? So 220 minus 108 is 112. So the object is right now at a height of 112, so I set that equal to the position equation, and I need to figure out what time did it hit 112 feet. So I solve, quadratic formula, solve, I get two values of t. I can't have negative time. That doesn't make sense in the context. So I just use my positive time, 1.995, and then I plug that into my velocity equation, which was the derivative of position again. Remember, so now I'm just finding an instantaneous velocity, but it's at this time of 1.995. Plug that in, I get negative 86.251 feet per second, so the ball is falling at 86.251 feet per second after 108 feet. Last one. To estimate the height of a building, a stone is dropped from the top of the building into a pool of water at ground level. How high in meters is the building if the splash is seen 6.8 seconds after the stone is dropped? You're using the same position equation. Pause the video, try this one on your own, unpause when you're ready to check. Alright, so here we answer in the context saying the height is approximately 226.576 meters. How do we come up with that? So here, we're using our position equation. A couple things. We're trying to find s sub 0, so we don't know that. The object is dropped, so that means the initial velocity is 0. I know that the time was 6.8 seconds. This was in meters we're trying to find, so I'm using the negative 9.8 as opposed to the negative 32.2. And this problem, we're actually not doing derivatives at all. So the point of this was to get you to remember, like, alright, we're not always doing the same stuff. This is something we did last semester, actually. So if I want to find, I know when it hit the ground is at a height of 0, so I can set this equal to 0, type this into my calculator. This is 0 anyway, just type this in, and I solve for the initial height. Pretty straightforward. Okay, a couple things we want to remember. Average rate of change is the change in distance over the change in time, so that's the slope between 2 points. Instantaneous rate of change is the derivative of the position function. The velocity is the same thing as the instantaneous rate of change, that is the derivative of the position function. The acceleration is the derivative of velocity, which we haven't talked about this yet, but that's what we call the second derivative of the position. That should kind of make sense, though, because the velocity is the derivative of position, and then the acceleration is the derivative of velocity, so therefore it would be the second derivative. Okay. That's it.